Okay, so let's go through this example. So we want to find the volume of the solid obtained by rotating the region enclosed by y equals ln x and x equals 3 about the line x equals 5 using washers and then using shells. So the first thing we have to do is to actually graph the region, and so first things first here, let's graph y equals ln x. Right, so y equals ln x just looks like this, right? Purposely drawing it, kind of short. So, intersects the x-axis there at x equals 1, right? And then we have the line x equals 3, right? So any equation x equals a constant is a vertical line, right? So let's do a different color. Blue. Right, so that's our line x equals 3. And we see that we have this region right here, enclosed here. And we're going to rotate that about the line x equals 5. We might also, before we finish the sketch, we might also just figure out kind of our limits, our intersection points. Right, so we already see that the curve y equals ln x intersects the x-axis here at 1, right? So if we're first doing the intersection points with respect to x, then it would clearly go from 0 to, or 1, sorry, 1 to 3. And then if we're looking for the limits or the intersection points with respect to y, right, then we're talking about first we have y going to be 0 here, right? And then going up to here where ln x meets x equals 3, right? So where does ln x intersect with x equals 3? Well, when x equals 3, y is equal to ln of 3. So ln of 3, right? Right. Right, clearly this is 3 over here. So, all right, so we're going to rotate that about the line x equals 5. Okay, so now we have the region rotated and sketched. So clearly this isn't the best representation of the solid. The solid itself is going to be, popping out of the screen here. Kind of vaguely looks like a, donut, maybe kind of cut in half, I guess. Right, but it's 3-dimensional and we're looking at a 2-dimensional screen, so this is just a cross section, right? So let's start with the method of washers, right? So when we use washers, we can view it in two kind of different ways. The first way that we learn it is by slicing the solid perpendicular to the axis of rotation. The axis of rotation is a vertical line, x equals 5, so slicing it perpendicular would be slicing it horizontally, like that. And, then what we would do is, this would be maybe a slice here, just yi here, right? And then we would just make these slices on even sub-intervals from, y equals 0 up to ln of 3, right? So just along that interval, right? So just kind of slicing it up all the way from y equals 0 to ln 3, we could approximate each of these slices by a washer. Right, but the other way that we can kind of view it is if instead of just slicing and then approximating the slices by washers, we could first just form these rectangles of equal width delta y, right, along this interval from 0 to ln of 3, and then rotating the rectangle about the axis of rotation here, we get washers, right? And so, viewing it these two different ways, it's the exact same thing, right? Struggling a little bit drawing a straight line. But viewing it as rotating rectangles might be a little bit of an easier approach. Okay, so we have the washer that's formed here. Outer kind of rim is gonna look like that, and then the inner is gonna look kind of like that, right? And it has this little thickness to it, right? Mark that. Right, it has that little thickness of delta y here, right? And we have to figure out the dimensions of the washer, right? So we have to figure out its inner and outer radius. So as you can see, the inner radius, right, let's use green for that, right, is just this, right there, so r inner, right? And that just corresponds to this distance here, right? That horizontal distance there. And that's constant, right? No matter where along this interval with respect to y, right, this highlighted interval here, that distance, that green distance, is going to be the same all up and down there, right? So it's the same here, it's the same here, right? It's the same everywhere, right? And what is it? Well, it's just 2, right? We're going from x equals 3 to x equals 5. That's just a distance of 2, right? So r inner is equal to 2, right? The thickness of our rectangle and then our washer also, indicates that we need to have everything, all of our dimensions in terms of y, right? Because delta y becomes dy when we go to integrate, and that is the variable that we integrate with respect to. So the first thing we might want to do here, maybe we could have done this a couple steps back, but is just get this, curve y equals ln x in the form, gy is equal to x, right? So we want to solve for x. How do we do that? Well, just take e to the power of both sides, right? Then you have e to the ln x just gives you x, right? E, the exponential function e to the x is the inverse function to the logarithmic function ln x, right? So you get x is equal to e to the y, right? Okay, so now we want to find the outer radius. Please, pink. So our outer radius, just on the washer down here, is this here, right? That's our outer, right? And so that's going to correspond to this distance here, right? And so what is that distance? Well, we have, let's maybe use a different color. Let's use orange. So we have that this, total distance here, right? What's that? Well, that's just 5, right? That's just the distance from the y-axis to x equals 5. And then this little distance, let's do yellow, right? This little distance from here to here, right, is just the, the horizontal distance to the function, right, from the y-axis, right? And we have x is equal to e to the y, right? So, right, this is the point here where we're touching the curve, right? So this is just e to the yi, right? This little yellow distance. I know these are very close in color, but the one above the other one, right? E to the yi, right? So then what is our pink distance, right? Well, so it's this big orange distance 5 minus that little yellow distance e to the yi. So just 5 minus e to the yi. right? And, you know, unlike the inner radius, this does depend on y, right? It depends on where we're at, right? Like if we're up here, that distance is going to be a lot smaller than if we're down here, right? Okay, so our outer is, I'm just going to put it down here. Our outer is 5 minus e to the y. Okay, so now volume is equal to the integral, you know, we're using washers, right? Is equal to the integral of the area of the face of the washer, right? dy. Because we're integrating with respect to y. We've already discussed that, right? Our thickness of our rectangle and washer is dy, or delta y. So, and our area of the face of the washer is, you know, pi r outer squared minus pi r inner squared. And we already have our limits of integration, or just our bounds here, 0 to ln 3. Our outer is 5 minus ey, quantity squared. And then our inner is just 2, and then we're going to square that. And so that's our integral. So I'm not going to actually compute this. This might be kind of similar to a homework problem, I think. But what you would want to do is, you know, expand this. And then you would have a term that's e to the 2y, and then do u sub for 2y, right? And you get du is equal to 2 dy, and then, you know, dy is equal to du over 2, and yada yada. Okay, so I'm not going to actually compute the integral. You could do that yourself. Now we're going to do this using the cylindrical shell method. So now we're going to do, this using the shell method. So now to use shells, and how this is different from washers, is we're going to form these rectangles that are parallel to the axis of rotation instead of perpendicular, right? So, you know, you can kind of remember it that way. You know, washers, we take, you know, perpendicular cross sections, or, you know, perpendicular rectangles, and then shells, we want to take parallel rectangles and then rotate them, right? So parallel to the axis of rotation, which is in this case a vertical line. So, right, so we're going to form these vertical rectangles, right? Do that a little bit better here. That's not better. There we go. So vertical rectangles of width delta x, right? Rotating that about the axis of rotation, which in this case is this vertical line, x equals 5. We're gonna get cylindrical shells, right? So what we, you know, do is we have, you know, what we're doing is, you know, kind of creating these shells from here, x equals 1 to x equals 3, right? And right, not the best drawing here, but you get the idea, hopefully, right? We're going to form these rectangles in the region here, and then rotate them around the axis of rotation to get these shells, right? And we're going to do that for x, from x equals 1 to x equals 3, right? So that's our interval there. Okay, so now let's draw the cylindrical shell that we're going to have here at, you know, xi, right? So again, I'll do this the best that I can here. Right, it's gonna look something like this. Right? And it's going to have these really thin walls, right, of with, you know, delta x. And it's going to have the height right there, right? And it's going to have a radius right there, right? And we know that the volume of a cylindrical shell is just equal to 2 pi times the radius, which 2 pi times the radius is the circumference, times the height, times the thickness, right? And the thickness is always, you know, delta y or dy or delta x or dx, right? So let's figure out what these dimensions are. Well, let's start with the height. So the height here just, you know, corresponds to the height of this rectangle, of course, and that is just the height of the curve, right? And at xi, right, so that is going to be ln xi. Right? And then the radius, right, is this distance here. And so that is going to be what? Well, so we know that this, let's see, smaller distance here, use orange, I guess, or maybe this color here. So we know that this distance here is just xi, right? So that's just xi, right? And then this total distance, what other color can we use? Purple. You know, this total distance here is 5, right? So this green, you know, distance is just that purple distance minus the orange distance, right? Do you see that? So that's just 5 minus xi. So the radius is 5 minus xi. Well, let's leave out the I, right? Because this is where we're going to actually plug into the integral. Okay, so that's everything we need, right? The thickness is delta x, which is going to become dx in the interval. Okay, so now let's set up the integral. Okay, so we have volume is equal to the integral from a to b, 2 pi r times height, times what's gonna, you know, we don't really need a times here, but, you know, what is our dx, right? That's our thickness. Okay, and we already figured out, you know, the interval for x is 1 to 3. R is 5 minus x. Height is ln x. Okay, so now I've set up the integral, but this integral is something that we're not actually going to be able to compute using the methods that we know as of right now. But this is something that we will be able to compute in the next section, in the next chapter. But specifically this integral we will be able to compute in once we learn the technique of 7.1, which is integration by parts. Okay.